So next talk will be given by Christopher Savoie from Zapata Computing. And the title of the talk will be Quantum Enhanced Machine Learning for Enterprise Applications. Chris?
Thank you very much. Yeah. Let me make sure that we're getting my screen up here in PowerPoint. See if I can find it here for us. Try one more time, launching. No. Hold on 1 second. It always doesn't work when you want it to, right?
Yep. Take your time.
Close this one. Close this one. And one more. Okay. And I'll try one more time again. There we go.
Great.
You see it now? Good?
Good, good.
Great. Finally. My apologies. And resume share. There we go. Bring your share to the front. Should be resume share. Can you, is it not changing yet? Sharing is paused. Please bring your shared window to the front. Are you seeing the changes in the screen?
Not really.
No, it's not changing. So hold on 1 second. I'm going to stop share and I'm going to resume share again. Share. There we go.
We see it. Great.
Great. There. So, thank you for having me. I want to thank the organizers for having me today to talk about quantum machine learning in the enterprise and some use cases in machine learning and optimization, particularly. I'm Christopher Savoie. I'm the CEO of Zapata Computing. We spun out of Harvard in 2017 from the lab of my colleague and partner in crime, Alon Asparagusic. Some of you who may know, his lab actually gave birth to the first NISQ quantum algorithm, VQE, that many of you who are involved in quantum would know about. Jared was the first author of papers now at Google, as you know. And he's trained a lot of people in near-term quantum algorithms, as some of you may know. So we spun out of his lab with the goal of using quantum computing to solve optimization, machine learning, and simulation problems across various industries. We are working with many top companies in many different industry verticals on these kind of algorithms, Fortune 500 companies mostly, one top 5 energy company, a top 5 food and beverages company, a top 5 chemical company, a top 50 finance company, on various problems across these industries. And so why quantum machine learning? So in machine learning in general, we represent data in some kind of a feature space. For example, movie length, genre, year, these different parameters we can have. Or in chemical space, we might have the bioactivity and the chemical descriptors. And basically, if you have more features that you want to see, you'll have more dimensions that you need to cover in this data space. And you can model this data, obviously, as a probability distribution. And like this, and we can, do all the things we can do with probability distributions, throw out outliers, try to be discriminatory with our probability distributions, etc., to describe this data space. So we can use this, obviously, to model real-world complex probability distributions. And some of the things we've seen, some of those distributions can be numbers, they can be stock trading things, they can be chemical systems and these kind of things. They can be faces or images, for example, that we see in machine learning when we're trying to model these real-world things. They could be handwritten digits. They could be spectra of various sorts that we're looking at. They could be chemicals. And the machine learning here has basically two different modes, if you want to think about it. There's a discriminative task. Is this, or does it fit this probability distribution or not? And then a generative task. Based on that probability distribution, can I create something that looks like that, or simulate something that looks like that, or find data or a data point that might look like that distribution or fit that distribution? So basically, the generative side of this, generative modeling with latent variables, we use this latent space, basically this compression. So we take a latent space, this compressed space, which is useful for learning the features or a compressed representation of the data, or the main features of a data set. So it's not all of the data. So we don't have to look at all of the data. We can look at just the discriminatory, if you will, features of that data. So a latent space can capture various patterns and structural similarities among the various points in your data space. And the distance then in that latent space, so the distance between points in that multidimensional space, can then convey similarity or differences between or among these different data points or groups of data points. So this is the basis of how we can use these functions to discriminate various things. So here's an example of how we might use it in the chemical space. So in the latent space of molecular design, we could take a direct approach. So, this is what we do when we run Schrödinger or Gaussian to look at a particular data point and look where it actually is, one by one, if you will. Or we can look at things in groups and the inverse of this and use a data distribution as a virtual screening and using the discriminative function as a filter. Or we can use different evolutionary strategies in generative models, so variational autoencoders, GANs, as I'll describe, to do the inverse of this in a different way, which is to use it as an actual optimization to try to find things that fit within a particular distribution, meaning that they share a similar functionality or a certain space that's in that latent space that is described by different variables that you're looking at. And the way we do this, basically, one of the functions that we use to do this is to use these variational autoencoders when you open up and peel the onion. And basically, you try to find a compressed, low-dimensional representation of the various inputs. And then from that, you can either use that for some other purpose, or you can use that to construct or reconstruct an output using a decoder that would fit that input. So by doing this, this is how the basis of how we might do deep faking. We take a particular distribution, we encode it, and then we can then decode that into something that's reconstructed and make something that looks like that. So we can use this in molecular discovery, for example, by simultaneously optimizing the autoencoder, and this will provide us with a property prediction model, the distribution that we'll use to describe that latent space. And that can provide, you can map that to a molecular representation, so a structure to function type of property prediction that we can do. We can use this also in the context of generative adversarial networks, the GANs, that I'd like to talk about today here. So you can do this classically. We can now take this latent space, represent it, have a discriminator, and then we can decide whether this came from the data that we've seen before, or this has been actually, if this was generated by another neural network, whether it actually is fake or real or fake. And we can use various gradient descent approaches to describe this. We can do this in molecular discovery. We have used this in molecular discovery classically. And we can also use it in things like anomaly detection. So this is just even classically, how can we use these generative adversarial networks without regard to quantum to do various things that are very useful in looking at various data spaces. Here, medical imaging, to detect anomalies like cancer or that kind of thing. And the popular techniques classically that we use for anomaly detection include density-based techniques, Bayesian networks, hidden Markov models, all these kinds of things. And we can use variants of this to do this, but we can also use these GAN models to find these distributions and find what these anomalies are. This is the classical way of doing that. And we can go into this. I don't have a lot of time to talk about the real innards of how this works. I have to abstract it quite a bit. But the potential here, these things are already being used. They're already in production. Many of the industrial companies are using some form of these neural networks, these deep learning techniques, particularly in the use of generative models, to do useful things already in big data settings and other settings. And what we want to talk about today, though, is the potential of quantum generative models and why quantum can add something to this. So quantum computers are particularly good at systematically generating and capturing rare, low probability events that are really hard to generate and capture classically. So for example, because of this, they can model probability distributions in a better way, in a more detailed way. And they can sample from probability. The reason they can do this is because they can sample from probability distributions better than classical computers. And we've heard about a bit about this supremacy experiment, and what it was actually a random sampling experiment to show that definitively and experimentally, that empirically, that the Google computer, and now recently the Chinese computer a couple of days ago, shows that you can take a random distribution and describe that better on a quantum system than you can on using a classical computer. You can arrive at that probability distribution much more quickly than you could arrive at it, that description using a classical technique. So what does this mean? That means that quantum computers will have access to more complex randomness than a classical computer. These were random circuits in the Google experiment. Quantum computers today are not large enough to solve very useful word problems using the discrete algorithms, as Will and others have described. But we can still tap into this potential of what we have today because of this particular randomized sampling capability that we've already shown has supremacy over classical computers. So because of this, quantum accessible events, or randomly accessible events, are a superset of what you can see classically. And so because of this, we can use this in the context of a hybrid quantum classical architecture to basically add to what we just showed you with the adversarial networks that are already in use today. So the way that we do this is we can add a quantum sampler into this already pre-existing architecture. And I'll kind of describe that on a very high level today. So these pictures are fake on the left. They may look like real people, but these were actually generated by a classical generative adversarial network, deep faking, if you will. They're not real. They look like something very real, but they were done on a classical computer using classical techniques. And these are handwritten digits that come from a data set that we have called the MNIST data set that we use to basically benchmark whether our inception scores on a classical neural network are doing well or not. This is just one set of data that we might use to do that assessment. And here, what we're doing is we are trying to, in this experiment, find out if we can make a handwritten digit like these in the MNIST dataset better than we could on a purely classical neural network by using this quantum random sampling capability that I described. So that was the state of the art in 2020 at the end. You can look at the paper, the archive references there. I can send it to you or put it in the chat later. But that was, this Chinese group did this. If you use your imagination really, really well, you can see those are ones in the 6th line there. But you really have to use your imagination. Not very good result, we would say, compared to classical networks. So what are we doing here? So the basic architecture is we have this a prior distribution. We use this prior probability distribution to load the generator, this neural network. And the neural network then takes a guess based on that distribution of what a handwritten digit or a face or a chemical might look like. And then you have another neural network on the other side that looks at your MNIST data set in this case, or whatever your real data is, and then tries to guess, am I being faked or not? Is that real or not? Is that real or fake? So it gives a binary output. And then in a classical system, we might use a Born machine or something to try and find a better distribution, to try to relearn what that distribution might be, and then reload the prior and take another guess. So that's generally how it works. Well, we can use a quantum circuit Born machine to do the same thing that we're doing classically there to learn the distribution. So here we will initialize a circuit with random parameters, as you might do, creating a random circuit like the Google experiment did, right? And then we will take a measurement from that randomized circuit. Then we will estimate the mismatch. This part is done classically. We will look at the distribution of the data that we want to learn, the expected distribution that we want, and we'll look at the outcome from the quantum circuit and try to then update the parameters and repeat 2 through 4 until we converge, and that the lines on the left start to look like the lines on the right. The distribution starts to match, and we try to get closer. By using this methodology and substituting that methodology here in the middle in the green box to do our learning, we hope to get some advantage over classical distributions because of the complexity that we talked about, the access to a maybe greater superset of correlations that we can discover in the data there. At least that was the hope. So here we used IonQ's 8-qubit, very modest 8-qubit machine to actually give us a bit string that would allow us to make this random sampling, and then use that as our distribution to load that prior. And here we go, and we compared this directly with a classical method. So you can see the IonQ 2 different experiments with different types of ANDs in the orange, you can see. And we compared that bit to bit with classical, and there you go, better guess, better guess, better, we hope, better, best. And there you go at the end. Much better than the original result that we just saw as the state of the art from last year. So we're getting actually, the interesting thing is, we're getting a statistically significantly better result with the quantum enhanced methodology by just substituting basically the quantum piece on finding that distribution than we can with a classical Born machine. So what this tells us is that bit for bit, we can get some advantage near term. And now we can use this capability. Oh, here we did it for handwritten digits, but we could use this same type of solution for other things. So why not use the same thing to look at derivative prices for stocks, for example? So here, in a separate paper that the reference is there, what we did was basically we created a GAN SPI, if you will, to a classical solver. And here what we're doing is we're taking the S&P 500 stocks, okay? And we're fixing the rate of return that we want to get. So we're fixing the cost function based on a rate of return that we expect. So that's a fixed variable that we put in there. And then we want to lower the risk. So we have a cost function that wants to give us the lowest risk we can with a combination of stocks that we select from that index that will give us the lowest risk with a given fixed rate of return. And the blue here are the outputs from a classical solver. That we let the classical solver give us those outputs, and then we try to find, using the quantum enhanced methodology, the distribution of those outputs. And when we learn the distribution, now we can deepfake. Now we can take a guess at a better solution in the orange that will fit that cost function using that same distribution. So now we can actually, before the blue even guesses it from the outputs that we've gotten from that solver, we can learn that distribution pretty accurately. And now before the blue even gets a chance, we can guess better solutions than the blue gives us by knowing its distribution. So we're deep faking better solutions than the actual classical solver is giving us by using this methodology, which we think is actually pretty cool. Because now we can actually use this in many areas. Here are stocks. You could imagine an insurance risk or other optimization, combinatorial optimization types of things where we might be able to use this. So we could boost performance of a customer's existing classical optimizer. If you have an optimizer that you're using or a solver that you're using, we can now learn the distribution of the output of that thing and actually fit in right into your legacy solution. So you give us a candidate solution and an output. We check if the candidate is optimal. We then use this quantum generative model to learn that distribution of the good candidates that we want and propose better candidates for the solution and then feed back into a kind of a closed loop optimization. So we can use this in generally others. So we've had oil and gas companies come to us now to try and use this for maybe optimizing a chemical process, for distribution of consumer goods. There are optimization processes that look very much like this open loop optimization that we can turn into a closed loop optimization. So we call this quantum enhanced advantage. So we can take any black box optimizer that you might have that you're already using, your classical one. We can work with any loss function and cost function, no matter how complicated it is. We don't need to evaluate gradients. And we can respect your proprietary code. We don't even need to know what your solver is. We just need to look at the outputs. So we can look at, for example, risk, return, combine risk and return, and give you a solution there. In portfolio optimization or logistics, where you want to optimize for time of travel or transportation costs. And basically, the advantages we have here, if you compare to things like greedy algorithms or gradient descents, these all have this local minima, which is the big problem that we all run into. And even in global search, we run into some problems. With simulated annealing, we always are greedy. We're always looking for something in the local vicinity. And even generative models model the space of the solutions and get us caught in here. But what we're doing here, we can use a quantum and quantum-inspired generative models that are showing us better results and hopefully get us to a more global minimum. In addition, an advantage is we can use long-term memory versus short-term memory here. And we can act as a booster to a pre-existing algorithm that you already have. And I'm running out of time here. So I think this summarizes it. QAOA is an optimizer that's used now in quantum, but it can't use a large number of variables right now. Can't use an arbitrary cost function, and it's not really data-driven. Same with quantum annealing. Other inspired quantum things you may hear about from Microsoft QIO can use a large number of variables, but they can't use an arbitrary cost function, and they're not really data-driven. QEO does all of these things, and we can use them for various uses in industry. Thank you very much. 감사합니다.
Thank you. Thank you very much, Chris. Yeah, the time is up, so we'll talk more about the Zapata in the panel session again. We thank Chris again. Yep.